Okay, in this video, we are going to have a look at FSK, frequency shift keying. Now in computers, in digital logic, we use binary ones and zeros, and in digital circuits, we use logic ones and zeros, and we represent them as voltage levels. So we have 0 volts for binary 0, and 5 volts for binary 1. Now sometimes we'll use 3.3 volts or as high as 10 volts, and we use these voltage levels, say in UART, so RS-232 or RS-485, or Ethernet, where we send these voltage levels down a copper pair to the destination. Now if we want to run data down an AC coupled line like a telephone line or over a radio, we cannot send voltages over a radio, so we have to code them in a certain way, and we use FSK. So we use mark and space frequencies. So we use audio frequencies, so we'll have a high tone for the mark or a digital 1, and a space which will be a low tone which will be a digital 0. Now we could send these audio signals over a radio, and that will be our digital 0 and 1s. Okay, here's my FSK generator circuit. Now this is audio FSK, and it starts off with a crystal oscillator, so it's very stable. So I'm using a CD4069 hex inverter to build a crystal oscillator. This is my tuning cap. And I have a divider, a CD4040, which is a ripple counter. And I'm using a diode matrix to divide down the crystal oscillator into audio frequencies. Now I turn those digital signals into analog signals, so square waves into sine waves using a CD4018. So I could turn on this circuit and I'll give you a mark frequency, which will be the high frequency. I'll go to the space, which will be the low frequency. So that'll be a digital 0, and this is a digital 1. Now I'll alternate between 1 and 0, and back to my mark frequency. So next we'll have a look at the block diagram schematic of this circuit. Okay, here's the block diagram of my FSK generator. So I have a 1 megahertz oscillator using a crystal and a CD4069 hex inverter. So I have 2 hex inverters, and I have a 1 megahertz crystal in a feedback path with a 4 to 40 picofarad tuning capacitor. So I have a 1 megahertz signal feeding my 4040 ripple counter, and that's going to divide the 1 megahertz crystal down into audio frequencies. So our input is serial, so it could come from a UART, so we have serial data feeding the 4040. So a logical 1 as data will divide the 4040 to give us a mark frequency, and a logical 0 as data will divide the 4040 to give us a low space frequency. And that's fed into the 4018 walking ring counter, and that's going to take the square waves and it's going to convert it into a chunky sine wave, which we've got 4 weighting resistors. And so our FSK output would feed a low-pass filter, and then we get a nice sine wave for our mark space frequencies. Now one important thing about this FSK generator, when we go from a mark to space frequency, we have to switch at the 0 crossing. So if we don't switch at the 0 crossing, like you see here, we're going to get a step voltage, and that's going to cause harmonics, and we'll have sidebands in our radio transmitter, which could cause problems. So it's important that we switch at the 0 crossing when you go from a mark to space frequency. Okay, next I am going to give some serial data to the FSK generator from a UART, and I'll give it 1 character, so it'll be 1 byte. So you'll hear the burst. So that's the burst. Now if we slow that down, this is what it sounds like in slow motion. And I'll go back to the normal speed. And if you look at the scope, you can see the burst of data, and if we zoom in, we can see that the transition from the mark to space frequency happens at the 0 crossing. That's very important. Okay, so we can modulate our FSK encoder with a UART signal, and here's the UART protocol. So it starts off with a start bit, which is a low to high transition. Then there's 8 data bits, then there's a parity bit, which is optional, and then the stop bit. Now the UART sends the data with the least significant bit first. So you can see here on the burst, we're going to have 10100000, and if we look at that as a byte, that's 00000101, which is hex 5. So actually we sent a hex 5 with this burst, and I made the amplitude of the mark and space frequencies different so we could actually tell the difference. Normally they'd be the same amplitude. So that's how we send a signal, and you can see in the bottom how it's decoded. That's our decoded UART output, and that will give us a hex 5 into our microcontroller. Okay, next, We are going to build an FSK generator using a CPLD. Now all the logical functions needed are available on the CPLD, and it has an onboard 50 MHz crystal, so we could use that as our clock. And I have an FTDI module, a USB to serial, connected up to the CPLD, and that will input our data. So I could actually send a text file into the FSK generator and we can monitor the output. So next we'll have a look at the schematic inside the CPLD of this FSK generator. Okay, I have Cordis 2 up and running on my computer, and you can see the schematic diagram of my FSK generator inside the CPLD. If you look at the very left, pin 12, that's our clock input, that's our 50 megahertz clock, and that's input into the LPM counter. Now this is a mega function counter, and it divides the 50 megahertz by 2604, so the output of this divider will be 19,201 hertz, and that's fed into the frequency divider chip into the clock. So we have two outputs of this frequency divider. We have a divide by 8 and a divide by 16. Now the divide by 8 will give us 2400 hertz, that's a mark, and a divide by 16 will give us 1200 hertz, and that's a space. Now the two outputs are fed into two NAND gates, and these are gating NAND gates, and they gate the appropriate frequency depending on the input data. So if the input data is a logical 0, it's going to enable the bottom NAND gate, and we'll get 1200 hertz out. And if the data input is a logical 1, it will enable the top NAND gate, and we'll get 2400 hertz out. Now the D flip-flop is there to synchronize the FSK output, so it always completes a frequency cycle. So it synchronizes it, so we'll always have a 0 crossing when we change states from a mark to a space. So next we're going to hook up the circuit, and we'll check out how it works. Okay, I got my CPLD powered up, and we could send some data in to the CPLD FSK generator through the FTDI module. So I have it hooked up to TerraTerm on my computer. And I'll actually send a text file, so I'll send it now. So you can hear the data being sent, the text file. So those are the data being sent, and if you look at the scope, you can see the transitions between the mark and space, that it completes a frequency cycle on its transition, so we have 0 crossing synchronization. Okay, now to decode an FSK signal. There are a couple of ways of doing it, and the one I'm using here is a phase lock loop. As you can see the IC here, I have a crystal oscillator for stability, and I got a tuning pot to tune the phase lock loop. So the phase lock loop locks onto the mark space frequencies, and the steering voltage to keep the phase lock loop in lock is the data output. Now there are other techniques. You could actually measure the period of the mark and space frequencies and determine the 0 and the 1 output. But I'm using the phase lock loop, and I won't go into too much detail. I might have to do another video on decoding, but that's basically the two ways which you could decode an FSK signal. Okay, we have been looking at audio FSK in this video because the mark space frequencies are in the audio spectrum. Now there's another type of audio FSK. It's called MSK, minimum shift keying. It's also called fast FSK. Now MSK is usually used in radio transmissions, and the key to MSK are the mark space frequencies. So if we have a mark frequency of 800 Hertz and a space frequency of 1200 Hertz, that will be MSK, that will be minimum shift keying. Now if we look at the period of the 800 Hertz signal, it's 555 microseconds. And if we take half the period, it would be 277.5 microseconds. Now if we add them together, so we have a period and a half, so we have 555 microseconds plus 277.5 microseconds. That will give us 833 microseconds, and that's the period of the 1200 Hertz. So by using these two frequencies, we have a very clean signal. It's very narrow band for radio transmission, so we have a modulation index of 0.5. So this is the purest signal that we could use for radio transmissions. Okay, we have been using the UART protocol to modulate the FSK encoder, and you saw in the scope my FSK burst, where I had a mark preamble that came up to the start bit, which is a high to low transition. Now when the detector detects the start bit, it will start sampling each bit center all the way along until it comes to the stop bit, then it will take in the data byte. Now we don't have to modulate the FSK encoder using the UART protocol. We could use our own bit stream. We could use Manchester encoding, where the data and the clock information is sent in the same bit stream. Okay, here's our Manchester encoder. It's just a simple exclusive OR gate. So we take our master clock and we feed it into one input, and we take our data and we feed it into the other input. Now the output will be the encoded data in Manchester format. So now the clock and the data information is mixed into one bit stream and sent over to the decoder. Now the decoder can extract the clock by using a phase lock loop and then decode the data. Now if we look at the data output, a logic 0 is a transition from 0 to 1 at the bit center, and a logic 1 is a transition from high to low at the bit center. So this encoded data output works very well for radio transmissions. Okay, if you're old enough to remember when trains had cabooses, this is what replaced the caboose. It's called an SPU, a sense and braking unit. It's a Canadian invention. It was invented here in British Columbia. I was involved with the project from day one. That's me back in the day. So this device is clamped onto the last car of the train, and it sends air pressure and motion information to the head end of the train. It uses a radio in the 450 to 470 megahertz band, and it uses FSK to send information to the head end of the train. So this is another example where we're still using FSK in radio transmissions.